So this is joint work with Samuel Simon, who was a graduate student at Simon Fraser University, but now has moved on into industry. I also want to thank Marnie Mishna because this all started at a mathematics research community event, and she was one of the mentors for that. And so she got us going on this project. So I'm going to remind you of a sort of graduate combinatorics course problem to begin with, just to give some context for what's going on here. And so, famously, the question of counting these paths that start at the point 0, 0, end at nn, and take steps right and up, and stay weakly above the line y equals x. Of course, these are counted by the Callan numbers, and there's multiple ways of deriving that formula. But I want to remind you of one of the classic ways of deriving that formula, which is instead of counting the paths that do stay above, you might consider the paths that actually do go below this line. And so here we have a path that goes below the line at two different points, or like twice, two different regions. And in order to count paths like this, we might pinpoint the first time when it goes below the line y equals x, flip the path from there on, and then we'll always end up with a path that's not too hard to show that ends at n plus 1 comma n minus 1. And that's bijection between the paths that go from 0, 0 to nn and do cross below, and any path from 0, 0 to n plus 1, n minus 1. And so that's convenient because then we can count those paths really easily. And overall, we know that the set of paths that stay above is all the paths minus these bad paths. And so then you get pretty quickly the formula for the Callan numbers. So one question that might be sort of natural after this is how much can this reflection principle idea be generalized, and what other families of lattice walks could we count by doing some sort of cancellation procedure or something like that? First, I want to justify why we might even care about any of these problems to begin with. Of course, the Dick paths are, in bijection with so many other objects that it's pretty clear why they are important. But even if you modify lattice paths so that they are slightly different, they still have bijections to a bunch of other objects, and trees, maps, permutations, lattice polygons, and so on are counted by them. Particularly important for the family of walks that I'll tell you about is the connections to Young tableau and representation theory. And so there's the Littleman path model, which does involve walks in file chambers. And so there are direct connections there between those walks and representation theory. Another thing is a lot of historically, the work on lattice paths has been done from a probabilistic perspective. And so along those lines, if you're tracking the endpoint of a lattice path, then you could view that as the sum of vectors that correspond to each step. And then you're really asking about potentially the distribution of a sum of random variables. Okay, I could then ask what sorts of things could we generalize from the Dick path model in order to get other lattice models. And so, of course, I could change my step set. And so previously we just had right steps and up steps, but why not allow other steps, potentially even steps with multiplicity if I want. I could also change the domain in which the walks are restricted to. And so for the Dick paths, they were restricted to a half plane, but really, for the Dick paths, I could view those as just one-dimensional because I could just sort of track the distance away from the line y equals x and leave the other direction off, and that would encode everything. But we could generalize these truly then to other paths in higher dimensions. And then we could also add weights to our paths. And so the weights you could add because maybe you want to add in a distribution into like probabilities into taking every step, for example, or maybe you do have multiplicities of steps, and weights is one way of accounting for that if you want to like think about colored steps, for example. Okay, and then historically, there's been a great deal of interaction between research in lattice paths and research in analytic combinatorics in several variables. It's often the case, like, ACSB has a lot of technical results, but in order to state the results, you often need to make some sort of assumptions about, for example, the singularities of your generating functions. And a lot of the starting results in ACSB do apply to broad classes of generating functions, but it is has been consistently true that lattice path models, like there always exists a model that breaks some of the rules for some of those theorems. And so then you have to develop new theorems in order to sort of address those cases. And so we will see a case that hadn't previously occurred in examples for those singularities popping up in this specific type of lattice walk as well. Okay, so I want to tell you about the specific type of walks that Sam and I looked at, and then we'll go back and give some more context afterwards. But we're going to be focused on these walks that are in this cone right here that extends off to the northeast forever. And then there's two models of steps here. It could either be the colored steps in the upper left, so that's northeast, northwest, and south, or it could be all six, so also including the dotted lines there. And then we're going to add weights to these steps according to the two sort of axes in the cone. And so anytime you take a northeast step, you'll add a weight of A. Anytime you take an up step, you'll add a weight of B. And those are multiplicative. Okay, and so if we're trying to just enumerate how many walks are there of length n in this cone according to those weights, then it turns out that we could get a bunch of different possible types of asymptotic formulas depending on what the weights are, but they are sort of broken into different regions depending on the weights again. And so, for example, if the weights are both quite small, and so in this context, that means less than 1, then in the lower left, that corresponds to that region right there. And we'll consistently get an exponential growth rate of 3 to the n, sub-exponential growth rate of n to the -4. And then also the constant term is explicit. It's just sort of gross for all of them, so I couldn't fit it in. But it is true. That's one of the benefits of ACSB is that you can get those constant terms, whereas some other methods have trouble with that. And so each of the regions here corresponds to sort of a different sub-exponential power and then also a different formula for the exponential growth rate. You could sort of see that the upper left and the lower right depend on only one of the weights, whereas the upper right region depends on both weights. And also the exponential growth rate is continuously varying between these regions. And so on any of the lines between the regions, the growth rate is given by either side because they're equal there. And then one thing that I'll get back to later is that currently the two, they're sort of hard to see as purple, but the lower and the upper left boxes right there and there are still conjectured because they do involve this singularity type that doesn't yet quite have results for it in the ACSB toolbox. Okay.
How the weight starts. Then you had 3 or 6 different types of step.
That's right, but I'm only tracking sort of overall how many times I went northeast or up overall in the path. And so for this given path, for example, I can see that I have to go up 4 times and northeast once. And so that would be b to the 4th a for the weight of that path, regardless of what steps it takes.
Oh, so up means either of those?
It does, yeah, they'll each end up. Well, no, I guess I have to be specific, but yeah, in this case, up meaning, like I guess you should consider how many times you have to go up first, and so that'll be 4, and then northeast from there, and that should uniquely determine any weights.
There's northeast, northwest, and south.
Mm-hmm. But the only thing I care about overall is the endpoints of the path. And so if I just look at the endpoint right there, then I'm just going to count how many times up first, and then, yeah. No, that's a good question. And so this is, like you could also consider, of course, weights on the individual steps, and then you wouldn't necessarily get the same weight regardless of each way you went to the path. But that is much more complicated, I think. And so these would be called central weights, where they only depend on that endpoint. But it is a good point, yes. Okay. So let me give you a little more context then about previous work on lattice walks. And so the one-dimensional case, considering walks, bridges, meanders, and excursions, which are whether you're above or below, or whether you're strictly above or allowed to go below, sort of the y-axis, x-axis, sorry. That's been covered by Cyril and Flageolet in the past. And then half-plane walks tend to be not tremendously more difficult in general than sort of the one-dimensional case. And the real jump in difficulty is when you start looking at the intersection of two half planes. And so often that's phrased in particular as walks in the quarter plane. And really the results for different walks in the quarter plane depend really specifically on the step sets that you're allowing. And so originally people looked at these walks sort of one case at a time, but then there were two sets of works that sort of developed unified frameworks for how you might approach these problems. Although even with the unified frameworks, you still have to do quite a bit of work depending on the step sets to figure out what's going on. Okay, and so overall, right, the analysis pipeline is going to be to come up with some sort of generating function that encodes the total number of walks of length n. I'm lying here a little bit because we will end up using multivariate generating functions because we'll represent things as the diagonal of multivariate generating functions. And then once we have that representation, we'll use ACSV to extract the asymptotics for these growth rates. And so as a reminder, there's a bunch of different classes of generating functions that might pop out when you do this sort of analysis. The simplest might be a rational generating function where the numerator and the denominator are both polynomials. Slightly worse than that is algebraic, where they satisfy a polynomial recursion or a polynomial equation, sorry. And then slightly worse than that potentially is if you have a rational diagonal. And so this would mean that the coefficients of the sequence you care about are encoded in a multivariate generating function among some of the terms in that. And the multivariate generating function is rational itself. And so that'll be the case that we're talking about mostly. But then you could have d-finite or things broader than that. And so one question might be, what sorts of things should I expect from lattice paths if I'm doing this sort of analysis? And it turns out that you can expect all sorts of things depending on the context. And so if you don't have any restrictions on your domain and it can go anywhere, then typically you're going to have a rational generating function, which is really from the sequence specification using your step set. If you have a half plane, then that'll end up being algebraic. And the problem for why things are so difficult as soon as you start adding more restrictions is that once you have the intersection of two half spaces, then you could have an algebraic generating function or something that's not algebraic but is d-finite or something that is none of those. And so that's implying both that the analysis is potentially very difficult and that the spectrum of like asymptotic forms that we could get is very broad. Okay. And so with that in mind, we want to sort of figure out which step sets might be easier to count. And Meltzer, Mishna, and Wilson had looked in particular at walks in the positive orthant of d-dimensional space and found that when the step sets were highly symmetric or almost highly symmetric, then that was more amenable to analysis easily. And then there also has been work on more general cone types, often from a probabilistic viewpoint. And so that in terms of ACSV has the challenge that some of the formulas that come out of here aren't as explicit as the ACSV formulas of sort of seeing the constant term, the exponential growth rate, and then the sub-exponential term. Instead, they're often phrased in terms of other functions or operators. And then another specific work that I want to make sure I mention is the work by Cortiel, Meltzer, Mishna, and Rochelle, which talked about weighted walks in the Gouilloux-Beauchamp model, where there they also found universality classes. And so our work is most similar to theirs in that sense that we end up with these universality classes with different weighted walks. Okay. And so part of the thing is I started at the beginning by hinting at this idea that there should be some sort of cancellation in order to count whatever you want to do. And we see that in dick paths. And then the question is, what sort of other walks might you see that in? And then there's sort of the hint from the last slide that when step sets are highly symmetric, that is one option for when things might work out well. Another option for that is to talk about Weyl groups and Weyl chambers. And so that's where we get to the Weyl chamber A2. But I'll throw up the definition of file group up here and a reduced root system. But the idea is that you start with some vectors, and then you're going to look at reflections defined by those vectors. And so for each vector, you'll look at the hyperplane perpendicular to that vector, and then you'll consider reflecting through that hyperplane. And then you'll have a root system as long as whenever you reflect one vector through the hyperplane perpendicular to another vector, you get another vector in your root system. And then we could talk about a reduced root system where we sort of have more minimal information that's encoding what's going on here. So that's not really as big a deal. But overall, if we have the group of all of these reflections, then it's called a file group. And so somehow these reflections are encoding maybe symmetries. And so we need to see how could I define a step set that is then like symmetric with respect to this group. And so the idea here is that we'll just pick a step set where if you use any of the reflections on any one of the individual steps in your step set, then you get back another step in your step set. Right? There's some other sort of technical things, but that's the intuition that's going on here. Okay, and so then I can show you in the middle, that's the diagram I showed you before with the walk. On the left is a diagram showing the root system for A2 in particular. And so this is defined by the unit vector alpha, which is just the vector 1, 0, and then the unit vector beta, which has an angle of pi over 3, and then the sum of those two, and then also their negatives. And then the dotted lines on the left correspond to the hyperplanes that we might reflect through. And then we can ask which step sets are symmetric with respect to these reflections. And it turns out that there's two sort of non-trivial step sets that are symmetric with respect to those reflections, which are the three arrows that we talked about originally, and then also adding those dotted lines to. And so there's really two models that we might consider as reflectable within this vial chamber. And so the vial chamber is the cone that's drawn in the middle. And those are called the tandem model and the double tandem, which has all 6 steps there. And one other note is that we could expand the cone out into the quarter plane on the right and then do this as a walk in the quarter plane as well. But the vial chamber approach sort of emphasizes how the symmetries might help us compute the generating function. Yeah. Okay, and so there has been previous work enumerating walks even within vial chambers as well. Although, again, a lot of those works have formulas that aren't quite as explicit because they involve determinants or other probabilistic functions. And then also Marty Mishna and my collaborator Sam Simon did analyze vial chamber walks in A1 to the D. And they were able to look at various dimensions there and find some nice patterns regardless of the dimension. Okay, and so again, these are the sort of results that we're trying to prove. Just finding the asymptotics for each one of these sections. And I want to, in the last few minutes, give a brief overview of how we might actually concretely do that. And so if we want to look for the generating function, there's sort of two options. One of them is to use either the kernel method or the generalized reflection principle by Gessel and Zeilberger. Those have already been used in the two-dimensional case to find the unweighted generating functions for these walks, although in higher dimensions, we can find the generating functions as well. And so if we already accept that the unweighted versions are there, then the weighted versions are sort of just evaluations of the unweighted versions. And so we get these two generating functions here for the 3-step model and the 6-step model. The denominator of both of them has multiple factors, which is sort of common for lattice path problems, but indicates that some of the singularities might be a little bit annoying. Right. Oh, and the other thing I wanted to mention, right, is that both of these, they encode the number of walks in the sense that if I look at the coefficient of x to the n, y to the n, t to the n, that is the number of walks of length n. Yeah. I don't think so. I think, yeah, these, well, maybe I guess I'm only looking at the positive coefficients. I think that's true. Yes. Could you say again? It should be rational. That's true. Although we could normalize it so it is, I guess. I think there is some cancellation though. I think so. But yeah, maybe we could talk. I can make sure. Okay, and so then of course, as per usual, we'll have the location of the smallest singularities determining the exponential growth rate and the behavior near those singularities determining the sub-exponential growth rate. But we'll have to do a little bit of work in analytic combinatorics in several variables in order to sort of identify what types of critical points are there. And so first we need to break down what types are possible and then identify what they actually are, and then refine to contributing critical points, and then we can use sort of existing readoff results. And so it turns out that this generating function, or those two, they only have two types of critical points, either smooth ones, meaning that locally the singular variety looks like a smooth manifold, or transverse critical points, which means that locally the singular variety looks like the intersection of hyperplanes whose gradients are linearly independent. The point being that the hyperplanes sort of don't look like each other, right, close to the singularity. And so all these conditions can be checked relatively easily algebraically. And so another thing which I would normally sweep under the rug, but is the thing that is different here, is that we also have to check for transverse critical points, whether or not they are contributing. And so that has a bit of a technical definition, but we're going to look at the denominator of my generating function, which is this polynomial h. I'm going to factor it, and I'm going to lump all the stuff that's not equal to 0 into h sub 0. And then all the other terms which are 0 at the critical point into separate factors, h1, h2, and so on. And then I need to look at the logarithmic gradients of each of these factors and normalize them. And then I need to look at the positive span of all of these vectors, which are, again, the normalized logarithmic gradients. So it's getting a little bit technical, but that's what you do. And so then I need to know whether the direction 1, 1, 1 is inside that normal cone or not. And if it is, then I can use existing readoff results. And so, for example, right, Pimentel and Wilson, or Pimentel, Wilson, and Meltzer, that textbook has lots of different categories of singularities, and you can sort of apply those results in order to get the asymptotics once you know what critical point matters. But the weird thing about this analysis here is that there is a critical point that is transverse, but also the numerator of the generating function vanishes at that critical point. And also at the same time, the direction 1, 1, 1 is at the boundary of the normal cone, which does not quite meet the conditions of the existing theorems. And so if I only had one of the last two bullet points, it would be fine. But both at the same time is an issue. And so we can verify numerically that this is just cutting the asymptotics in half, but we haven't quite proved it yet. But the next steps are now working with Steve Meltzer and his student Alex Kreuter to verify this conjecture is really true in these cases. And then hopefully after that, we'll be able to extend to other dimensions of this Weyl chamber or other Weyl chambers, with the goal in the long run of sort of analyzing all the Weyl chambers and blocks within them. Right. Thank you for your time.
Just a quick comment. Robin came to this community and said, you should try these techniques. And if you run into a problem, call us. And you're the first person that I've seen that actually.
So something which is, I think, never working is if you have some weights which are not symmetrical in your jumps. So do you know any way to handle this? So when the weights are not symmetrical.
I think I agree that that is difficult, and so I don't really have a good answer, I think.
So no hope to deal with this.
I think you're talking sort of about when the weights are not central then, right? Yeah, I don't know. I think that that's hard in general.
I just want to ask your approach, but well, for your work, the symmetry of the wave chamber is important. And do you said that you can do it on other wave groups? And do you think that for other types there would be a difference in the analysis, or everything would just work?
Um, well, so one thing I could say is some of the results here are already becoming computationally difficult, even though they're theoretically possible. And so, like computing the leading terms is taking a lot of time, like in Sage to do. And so, I think that that will probably be the holdup for a lot of progress in the future, I guess.
Okay, so you didn't start it on type B, type D, etc. You didn't start it yet. So, but it's
Well, there is some existing work on type B from Thomas Farrell, although I think that that doesn't have, like, again, it's from a probabilistic viewpoint, and so it doesn't have like the constant, the exponential growth rate and so on.
Yeah,
But other than that, I don't think there's anything yet. Yeah.
okay. Thank you.